All right, so last time we talked about the sum and difference identities for sine and cosine, and now we have to take care of tangent. So what we're going to do is we're actually going to go through and derive the sum and difference identity for tangent. And it's really easy because we just use the definition of what tangent is. Tangent is considered sine divided by cosine. So if we want the tangent of alpha plus beta, that's going to be the same as sine of alpha plus beta divided by the cosine of alpha plus beta. So after that, we are just going to substitute in each of these identities. So we fill that in. And next, unless you actually know what the identity is, you probably wouldn't think to do this next step. But what we're going to do is we're going to multiply this fraction by 1, but it's just going to be a fancy one, and it's going to look like this. And this looks weird, and why didn't I just do cosine alpha cosine beta divided by cosine alpha cosine beta, right? Well, the idea is that we want to create each of these four things to be fractions, because we know that tangent can be expressed as a fraction with sine and cosine. So we're trying to kind of work backwards into creating expressions that have tangent in it. So if I take this 1 divided by cosine alpha cosine beta and distribute to each of these, and then I take this one and distribute to each of these, you get this big old mess. And everything has fractions with the exception of this, and that's because what we divided by was this exact expression, cosine alpha cosine beta. So cosine alpha cosine beta divided by cosine alpha cosine beta gets you 1. So now what you're going to do is you're going to go through here and recognize that this cosine beta and this cosine beta cancel out. And then over here, this cosine alpha and this cosine alpha cancel out. But what you should also be recognizing is that this right here, this expression, the sine of alpha over the cosine of alpha, that right there is tangent alpha. Likewise, over here, the sine of beta over the cosine of beta, that's tangent of beta. And then down below, we have a sine alpha over cosine alpha, and then we have another sine beta over the cosine of beta. So each of these are tangent as well. So once you get through canceling and combining to make tangents, you get this expression, which is the identity for the sum with tangent. Now you can go through and do this exact same exercise, switching this plus sign to a minus sign, so these are minus signs, and that's going to switch these around as well. But you end up getting the same exact process, and then you get your two sum and difference identities for tangent. So that's what we're going to be using today. Now the thing is, unfortunately, when you use them, it's a little bit more complicated than when we were working with sine and cosine, just a simplification process. So let's go through and take a look at a couple of those. So first of all, we have tangent of theta plus 30. We are going to express this as an answer that has tangent of theta in it, obviously. And when we apply our identity, we get tangent of theta plus the tangent of 30 divided by 1 minus the tangent of theta times the tangent of 30. Please make sure that you are multiplying these together. It's a very common mistake. Okay, so now what you're going to do is look on your unit circle at 30 degrees or pi over 6 radians. And to use your unit circle and figure out what the tangent of 30 degrees is, take the sine and divide it by cosine. So the value of the y-coordinate divided by the value of the x-coordinate. And technically, since the denominators are the same, we only have to look at the numerators. So tangent of 30 is 1 over root 3, if you look at your unit circle. And of course, we want to rationalize that, so that's going to be root 3 over 3. So I'm going to replace tangent of 30 with root 3 over 3. So we get this big old mess. So how do we clean this up? We want to make it look pretty. This is not pretty. So to make this look nice, we're going to do our little shortcut here, because we have a complex fraction, fractions within fractions. I'm going to multiply the top and bottom by 3, since that's the LCD for all 4 of these terms. So if I multiply the top by 3 and the bottom by 3, this is what I get. And notice that I moved this radical 3 into the front part of tangent theta, so it doesn't look like I'm multiplying it to theta. And this is as far as we're going to go, folks. If you have an answer with the expression of tangent theta in it, you do not have to rationalize the denominator of your final answer. We could just leave it as is. Okay, so let's try one where you had something in place of theta. So let's say we had the tangent of 15 degrees that we needed to evaluate. Well, from before our last section, we know 15 degrees can be made by 45 degrees minus 30 degrees. So if we apply that tangent identity, the difference identity, we get tangent of 45 minus the tangent of 30 over 1 plus tangent of 45 times the tangent of 30. Okay, so now when you look at the unit circle, the tangent of 45, hopefully you realize that that's 1, and we've already established that this is going to be root 3 over 3. So when we plug this in, now we have another messy fraction, but we do have to simplify this and rationalize the denominator and all that good stuff. So the first thing, just like we did over here, we're going to multiply by 3 over 3, and that gets us this expression. And if you recall, how do you rationalize a denominator that has something like this? You're going to multiply the top and bottom by the conjugate. So the conjugate of 3 plus root 3 is going to be 3 minus root 3. So we multiply the top and bottom by that. When we multiply this out, multiply that out, this is what we end up getting. And if we combine like terms, combine these, we end up getting 12 minus 6 root 3 over 6. And then the 6 can cancel with the 12 and the minus 6. So we get an answer of 2 minus root 3. And that will be our final answer. Okay, so that is how you deal with your sum and difference identities for tangents. All right, that will be all for that section. See you later.